So from today onwards, we'll be starting our second module, elementary concepts of magnetic circuits, electromagnetic induction EMI, and AC fundamentals. AC means alternating current fundamental. So second module actually is having three parts. One is the basic concepts of magnetic field. This part we will be learning the fundamental concepts about the magnetic circuit. The second part is about the electromagnetic induction, and the third part is AC fundamentals. Okay, and I hope that most of the things in this magnetic circuit basics and electromagnetic induction, and even in the AC fundamentals, that you might have learned in 12th classes. So there is nothing much. It's not very complex, it's very simple. You just have to learn some definitions, certain formulas, and apply those formulas to do some kind of numerical examples. And doing that, you have to learn the concept, okay, rather than just by hearting it. You have to understand the concept behind it. So we will start with the first part. We will learn these elementary concepts of magnetic field circuit first. Okay, so the basics of magnet, or the basics of magnetics, you might have learned. The thing is that if you hang a permanent magnet, something like this, immediately we can see that one end of this magnet will be aligned to the north pole of earth. Immediately one end always aligned to the north pole of earth. So we will call that end is the north seeking end of the magnet. The other end is the south seeking end of the magnet. Or normally we call it as the north pole of the magnet, and this is the south pole of the magnet. But the meaning is this is the north seeking end of the magnet. And similarly this is the south seeking end of the magnet. Okay, it seeks the north pole of earth, that's the meaning. So a magnet is having north pole and its south pole, that is the fundamental thing. And we are going to learn different terminologies now. So the first one being, what is the meaning of a magnetic field? So if you take a permanent bare magnet with its north seeking end and its south seeking end, so we can see that magnetic field is simply the space around this magnet. The space around this magnet is known as the magnetic field. Okay, and you also learned in 12th classes that when you keep a magnet like this, the space around it, actually the reason is that there are magnetic lines of force. Okay, we start at its north pole like this, reaches the south pole, form a closed loop, and continues back to north pole like this. Similarly, there are many lines. So these things are called the magnetic lines. So the space around the magnet is called magnetic field, and these are called magnetic lines of force. Okay, and the collection of these lines and all these lines, it is called magnetic flux. When you add all the magnetic lines, we will call it as a magnetic flux. So these are the general terms that we need to understand. Once again I am telling, the magnetic field means the space around this magnet, and we can see the magnetic lines from north to south. It is aligned in such a way that it is aligned in this way, and this collection of these lines, normally we call it as the magnetic flux. And you have to understand this, that these magnetic lines, These are not physical lines, these are purely imaginary lines. Okay, just for the analysis or for the easy understanding, we assume that we are drawing these lines. Actually they are not physical, these are pure imaginary lines, but we can feel the presence there. When you keep a magnet, we can feel definitely the presence, we cannot see the lines. Okay, so we learned 3 terms: magnetic field, magnetic lines of force, and what is magnetic flux. Okay, and normally magnetic flux is normally represented by the letter phi. Okay, it's the total number of lines produced from a magnet, and its unit is Weber. Normally we represent by the letter WB. So this is magnetic flux. Another term that we need to learn is, if we know what is magnetic flux, then what is magnetic flux density? Density is always related to area, right? So number of flux present in an area, normally we can say like this. Okay, magnetic flux density is the flux per area. So if you take one area, how much is the flux in that area? That is magnetic flux density, and is normally represented by the letter B. So B is equal to flux per area, so phi divided by A. The unit of phi is equal to Weber. The unit of area is meter square. So the unit of magnetic flux density will be Weber per meter square. Or this Weber per meter square is sometimes termed as Tesla. Its another unit is Tesla. Hope you understood magnetic flux density and magnetic flux, what is magnetic field, and what are magnetic lines, and all these things are same when we call them by different name. That's all. Then another interesting feature is that if you place a steel conductor like this, and if I allow a current to pass through this conductor by using a battery, this is EMF, a current will be passing through this. So definitely we can say that a magnetic field will be produced around this. A magnetic field will be produced around this conductor. So this is one of the interesting properties. A current carrying conductor always produces magnetic field around it. Okay, so this magnetic field can be more stronger if we place a solenoid like this. So turns are wound here, so the magnetic field will be more if we keep a solenoid here. That all we know. And another term that you might have learned also about a toroid, a round steel core, and assume that this is a steel core, and I have certain wires wound here like this. So with the help of a battery, I am going to supply some current here, and assume that this there are n number of turns here, and immediately we can see that the magnetic lines will be formed like this. It forms a closed path, and okay, let L be the mean length of this magnetic circuit. Okay, so if you know like this, the next thing is that we need to learn is, what is the meaning of MMF? Magnetomotive force. Magnetomotive force, or MMF. So MMF is analogous to EMF in electrical circuit. What is EMF? Suppose that there is a circuit like this. E is the EMF, R is the resistance, and I is the current through. The force which drives this current through the circuit is called EMF. This battery is the driving force behind current. Similarly, there is a term in a magnetic circuit that is called EMF. So first of all, you need to understand what is the meaning of a magnetic circuit. The magnetic circuit, the definition is the complete closed path followed by any group of magnetic flux lines is called a magnetic circuit. The complete closed path followed by any group of magnetic flux lines. Any group of magnetic flux lines is called a magnetic circuit. So this toroid, this is a magnetic circuit. The complete path followed by the flux lines is called a magnetic circuit. So similarly, analogous to EMF, there is one force in a magnetic circuit which is called EMF, and EMF is the driving force behind the magnetic flux lines. Okay, so can I write it? I can write this definition for this MMF now. MMF is equal to the magnetic flux in a circuit is due to the presence of MMF or magnetomotive force, we can say. Similar to current in electrical circuit, here the flux lines are produced because of the presence of MMF or the magnetomotive force. So in this toroid case itself, for any circuit, the MMF normally we represented by letter F. This MMF is equal to, assume that this toroid is having n number of turns and I is the total current passing through this. So what is the force? N number of turns times the current, N into I. Number of turns times the current, that is a force which produces the flux lines. So this example itself you can see what are the causes of this magnetic flux lines inside the toroid. It is the current. Okay, and the number of lines depends upon what? The number of turns also. So this N into I is always equal to MMF. Okay, now let's see the unit of this MMF. MMF is normally represented by the letter F, and let's see what is the unit of this MMF. The unit of current will be ampere. These are the number of turns. So normally the unit of MMF is represented by ampere turns. Ampere turns. Okay, and normally this turns is not having any dimension, so simply we call ampere also. So anyway, the unit of MMF is ampere turns. Okay, now another term is that once we have learned MMF, I'm going to introduce another term. What is the MMF or the magnetomotive force per meter length in a magnetic circuit? What is the MMF per meter length? That is, MMF is N into I. L is the length of the circuit, so MMF in a particular length, how much is the MMF? That's the meaning. That is termed as the magnetic field strength, denoted by the letter H. MMF per unit length. How much is the MMF acting in a short area, short length? That is known as the field strength. So what is the unit of this field strength? H is equal to Ni divided by L. Ni unit is ampere turns. Length unit is meter. So ampere turns per meter is the unit of field strength or the field intensity. Or this Ni, normally what is Ni? This MMF. MMF is represented by the letter F. So H is equal to F by L. is the another equation that you need to study, because a lot of numerical examples can be asked based on this. These are very simple, just learn the concept and try to understand the formula and apply it. That's all. Now one other term that we are going to study is different materials. You might have learned that different materials allow magnetic flux lines in a different manner. Wood may not allow the magnetic flux to pass through, but a steel definitely will allow the magnetic lines to pass through it. Okay, so based on that, we are going to define another term which is known as the permeability of a magnetic circuit. What is permeability? It's normally represented by the letter mu. The ability of a material like wood or a steel or a medium like air, the ability of that material to become magnetized when placed in an external magnetic field is known as permeability. Or ability of that medium to pass through the flux is termed as permeability. Ability of a material or medium to become magnetized when placed in an external field is known as the permeability. Okay, so the equation that relating this is the magnetic flux density B is directly proportional to the field strength. If flux density increases, the field strength also increases. So it is replaced by this proportional thing is replaced by the constant B is equal to mu into H, and this mu is known as the permeability of the materials. Okay, so if you have this field intensity, field strength, you multiply with the mu, that is the permeability of that medium or the material, then you get the flux density in that medium. B is equal to mu H. B is equal to mu H, or mu is equal to B divided by H. You can write like this. This is another equation that you need to learn. Okay, so once you learn permeability, another term that we need to learn is what is the meaning of relative permeability. Relative permeability, which is denoted by the letter mu r. So from the term relative means it is relative to something. We are going to compare permeability of a medium relative to another medium. So the medium that we are taking as a standard is that of the vacuum. Permeability of vacuum, that is the reference term that we are taking. So mu r, the definition, that is flux density in the medium divided by flux density in vacuum. Flux density in the medium divided by flux density in vacuum. So mu r is equal to, flux density in the medium is represented by mu, and flux density in vacuum is denoted by mu 0. So the equation flux density in any medium is another expression is mu is equal to mu r into mu 0, and the value of mu 0, that is the permeability of vacuum or free space, that is equal to 4 pi into 10 raised to minus 7 Henry per meter. So all these things are basics. I know that you might have learned in 12th classes this thing. And so the next class onwards we will study another important term like reluctance. What are the properties of reluctance and features of these electric and magnetic circuits, etc. And we'll also try to do some numerical examples also.